Hello everyone, I am Chen Xusheng from the University of Hong Kong. Today, I present Dust, the first serializable database that can achieve both low tail latency and high scalability in edge computing. This work is collaborative with Hao Zesong, Jian Yujiang, Chao Yiruan, Cheng Li, Sen Wang, Gong Zhang, Ruino Cheng, and my supervisor, He Mingcui. Edge computing is a fast-developing computing paradigm that moves the computation results from the core data centers far away from clients to the edge of the internet that is close to clients, so that it can exploit clients' data locality and provide low client perceived latency. Edge computing is already widely deployed in many use cases, like the CDN networks, to improve user experience. Recently, with the development of the ultra-reliable and low-latency communication technologies like the 5G network, a new class of edge computing applications that deal with mission-critical tasks emerges. For instance, a NASA project tries to integrate the management of UAV networks and the management of normal airplanes to schedule air traffic and to avoid collisions among them. These mission-critical applications desire very low tail latency for a stable response time, and at the same time, their rigorous correctness requires serializable transactional support, because serializability is the strongest isolation level and can avoid many application-level bugs. However, as existing edge computing databases target only non-mission critical use cases like the CDN networks, they provide only weak isolation guarantees. To meet this new trend, in this project, we build a distributed edge computing database that can ensure both low tail latency and serializability. Different from traditional databases, in a typical edge computing database, nodes and clients are divided into regions, and nodes in the region manage only data shards that are most frequently accessed by intra-region clients. The intra-region networks are usually much faster than cross-region networks, so the replication is usually done within each region for low latency. In such a deployment model, client transactions can be divided into two categories. We call a transaction an IRT if it accesses only data shards in this region. Otherwise, we call it a CRT. Because typical edge computing applications show good locality, IRTs take a great portion of all transactions. Under such a deployment model, we summarize three technical requirements for an edge computing database that ensures serializability and low tail latency. First, when a cross-region transaction is under coordination, subsequent IRTs should not be blocked. Because the average latency for IRTs is only a few tenths of milliseconds, but the latency of CRTs can be hundreds of milliseconds. If IRTs are blocked, their tail latency will be very high. Second, a CRT should not be aborted on conflicts. A naive approach to meet R1 is to abort a CRT whenever it conflicts with IRTs. However, because in the lifetime of the CRT, many IRTs can be submitted and finished. Such a design will cause CRTs to be repeatedly aborted and stalled. Moreover, if an IRT sees the intermediate result of a CRT, the IRT must be blocked to wait for the commit result of the CRT before it can get committed. Third, as an edge computing application may have up to hundreds of regions, the database performance should be scalable to a large number of regions. Although there are many influential geo-distributed serializable databases that can achieve good performance when deployed among a few core data centers, they are not designed to meet the three requirements if deployed on the edge. A key reason is that these systems order transactions in a first-come, first-served manner, based on transactions arrival order at replicas or a central ordering service. These systems can be divided into two categories. The first category takes the deferred update approach, where transactions are first executed locally and then verified globally. However, such an approach generally cannot meet R2, as CRTs can get repeatedly aborted at the verification phase. The second category takes the SMR approach, where transactions are first assigned an order and then execute at relevant nodes according to this order. However, such an approach cannot meet R1. We use a simple example to demonstrate the reason. These are the time axes for two objects A and B in two regions. Suppose the CRT that sets the value of B to A+1 is submitted and coordinated using a standard two-phase commit protocol. After object A prepares the CRT, an IRT is submitted to object A, but this IRT must be blocked until the CRT finishes. Moreover, due to partial replication, region 2 does not hold a replica of A, so when object B is waiting for the read value of A and an IRT arrives, the IRT must be blocked as well. Note that such blockings are not critical in traditional geo-distributed databases because all transactions' planned perceived latency is already high. But in an edge computing database, if an IRT is blocked, its latency will be tens of times higher. To address this problem, in this paper, we present a new conceptual method DUST, decentralized anticipation and stretch. DUST also takes the SMR approach, but DUST order transactions based on when transactions' coordinations are anticipated to have finished and they are ready to execute. Conceptually, in the previous example, DUST assigns an anticipated timestamp 200 to the CRT and assigns the subsequent IRT1 a smaller timestamp 120. By doing so, although the IRT arrives later, it is ordered before the CRT without being blocked. Note that this is not a single local reordering, because region 1 can have many data shards with replication, and IRTs can access multiple intra-region shards. Doing a simple local reordering cannot ensure consistency. To handle blocks caused by inaccurate anticipation and cross-region data race, thus dynamically stretch the granularity of timestamps. For instance, when object B is waiting for the value of A to execute CRT1 at timestamp 200, it stretches out its granularity of clocks after its clock passing 199 and assigns timestamp 199.1 to IRT2 and assigns timestamp 199.2 to subsequent IRTs, avoids them getting blocked. A key challenge to realize the conceptual method of DUST is to anticipate a proper timestamp for a CRT without involving a central service for ensuring scalability. The timestamp must be in the future of all participating nodes' clocks to avoid the CRT getting aborted. But the timestamp cannot be conservatively large for the CRT's own latency. A stronger approach is to let a single node, such as the coordinator, solely determine a future timestamp. However, when the CRT arrives at its participating nodes, their clocks may have already passed the timestamp due to clock skewness or due to network instability, causing the CRT being aborted. To address this challenge, we propose a new two-phase anticipation protocol that complies with standard two-phase commit. Consider three objects A, B, C in three regions and the CRT accessing these three objects. For simplicity, we assume that network is stable, their clocks are synchronized, but DUST does not need such assumptions in its protocol. In the first phase, each node anticipates a future timestamp based on the RTT between itself and the coordinator B, representing when it can receive the commit message for T1. Each node also promises not to execute transactions with timestamps larger than its anticipated timestamp to avoid T1 getting aborted. In the second phase, the coordinator B selects the maximum anticipated timestamp TS max and commit T1 with it. T1 is committed with the maximum anticipated timestamp, implies that all participating nodes promise not to execute transaction larger than TS max, so T1 will not get aborted. A problem here is that if we look at the time axis of object A promised not to execute transaction larger than 200, but it can only receive the commit message at time 220. What if IRTs arrive during this time? This is exactly why we need DUST hybrid clock. Object A can start to stretch its timestamp granularity after its clock passed 199 because it knows it has promised not to pass 200, and it can assign subsequent IRTs the timestamp 199.1, 199.2, etc. to avoid them getting blocked. Overall, our new protocol does not need any central service, and it is based on the two-phase commit to achieve the minimal number of round trips for CRTs. Thus ensures one-copy serializability and no stale risk. To achieve this guarantee, thus ensures the following key correctness invariant. When a node N is executing a transaction T with timestamp TS, N must have executed all relevant transactions with timestamp smaller than TS. By ensuring this invariant, we can deduce that all edges in the dependency graph are in ascending timestamp order. This ensures two key features. First, the global dependency graph has no cycles, which infers serializability according to the serializability theory. Second, each node must have a complete history when executing transaction T, which infers that all read will read the latest write without any staleness. To ensure this invariant, N must be aware of all relevant transactions whose timestamps are smaller than TS. The key challenge here is that these transactions may not even be generated due to clock skewness. Existing traditional geo-distributed database address this problem by maintaining a system-wide watermark, and N can execute T if the watermark is larger than T's timestamp, because no new transactions preceding T will be generated. This approach can ensure very high throughput in traditional geo-distributed database. However, this approach will also cause very high latency for IRTs, because executing an IRT needs to wait all nodes clock past the IRT's timestamp. In thus, each node only tracks the clocks of intra-region nodes. This is enabled by thus new two-phase anticipation protocol. Recall that in the two-phase anticipation protocol, if a CRT accesses a region and may conflict with T, the CRT's timestamp must be larger than all participating nodes' clock. Therefore, by only knowing that all intra-region nodes clock past TS and all transactions coordinated by these intra-region nodes are well received, N can predicate that it is safe to start to execute T. To handle node failures, thus distinguishes the process of fast failover that removes suspected failed node and the process of asynchronous failure recovery that adds by the replica. When adding a replica, a challenge is how to set the clock of the newly added replica. For correctness, the new replica's clock must be larger than all nodes execute transactions timestamps, so that the new replica will not propose a transaction in the past and breaks thus correctness. However, when the replica is being added, other nodes keeps executing transactions, so their executed transactions timestamps keeps increasing, and we do not want to pause the normal transaction processing to add replica because the application may deal with some mission-critical tasks. To solve this problem, we model the process of adding a replica as a special CRT that accesses all nodes in this region and uses thus hybrid clock with stretchable granularity to minimize the disturbance of normal transaction processing. We provide a detailed description of the protocol with pseudocode in our paper. Overall, thus ensures the three crucial technical requirements and ensures serializability. To ensure R1, thus assign CRT's future timestamps representing when they can execute and use the hybrid clock with stretchable granularity for handling inaccurate anticipation or cross-region reads. To ensure R2, thus use the SMR approach, and thus two-phase anticipation protocol ensures that a CRT's timestamp is larger than the clocks of participant nodes, so it will not be aborted due to clock skewness and network instability. Thus, it's also scalable to the number of regions because committing a transaction only involves participating regions. Thus also ensures serializability with no stale race. We have a proof of thus guarantee in our paper. Compared to existing work, thus is the first distributed system that can meet all the three requirements and serializability. While existing traditional geo-replicated databases are not designed to meet these three technical requirements when deployed on the edge, and existing databases for edge computing target only non-mission critical scenarios, so they do not provide serializability. Dust is substantially evaluated, and our evaluation earns the result reproduced badge from the committee. We chose TPCC payment only, and TPCA as our benchmark suite. We choose TPCC as the major benchmark because it is standardized and well understood. It also shows good spatial locality, and it is evaluated by our baseline systems. Although TPCC is not dedicated for edge computing, it covers diverse rewrite patterns that are common in edge computing. We compare Dust with through influential traditional geo-distributed database that ensures serializability. All systems were implemented on the Genus code base, running the same set of stored procedures on the same in-memory DB. Our evaluation focused on 6 evaluation questions to test Dust performance on different settings and different workloads. Due to time limit, we only cover 3 of them. For the rest of the evaluation questions and more detailed analysis for our evaluation results, please refer to our paper. We first compare Dust and the 3 baseline systems under the default TPCC workload. We run 10 regions and 10 shots per region with the replication level of 3, and we change the number of clients per region. The evaluation shows that Dust greatly reduced the latency of both IRTs and CRTs, and at the same time, Dust throughput is comparable to the baseline system. Among these 3 baseline systems, Genus and S-log take the MSR approach, and their IRT's tail latency was higher than Dust because IRT may be blocked by CRTs if these systems are deployed in an edge deployment model, but such blockings do not exist in Dust. Taper takes the deferred update optimistic approach, so its tail latency is high on contented workload like TPCC. Our evaluation result for Taper is the same as the evaluation result for Taper in other papers. To evaluate the scalability of Dust of baseline systems, we select a number of clients that make each system meet its peak throughput and change the number of regions. Among these 4 systems, Dust, Taper, and Genus achieve good scalability because in these systems, coordinating a CRT only involves relevant regions, and coordinating an IRT only involves intra-region nodes. Well, S-log is designed for being deployed a few core data centers, so when the total number of regions is large, the central ordering service in S-log can easily become the bottleneck. To test Dust robustness, we did 2 experiments. In the first experiment, we let the cross-region RTT to fluctuate as 100 plus or minus X milliseconds. As shown by the top 2 figures, IRT's median and tail latency was stable because IRT was coordinated within each region in Dust, and inaccurate anticipation is already handled by Dust hybrid clock. CRT's median and tail latency increase roughly linearly, which is as expected because the network communication time for CRT did increase. The overall throughput only dropped a little because more throughput was contributed by IRTs. In the second experiment, instead of letting the RTT fluctuate among a stable value, we subtly changed the RTT at each vertical dotted line to mimic the effect of network spikes. As shown in the figure, IRT's latency was still stable. When the RTT dropped, the drop of CRT's latency fell behind a little because Dust used the average RTT of recent communication to anticipate timestamp of CRTs. Overall, Dust performance was stable on cross-region network anomalies. Now we conclude. Dust is the first edge computing database that ensures serializability, low tail latency, and high scalability. It has the potential to support the deployment of many emerging mission-critical edge computing applications, like real-time traffic management systems, health monitoring system, and edge computing-based trading and retailing system. Our artifact is evaluated by the Artifact Evaluation Committee, and it is accessible from the GitHub. Thank you all for listening, and I'm happy to take questions.